Alright, so today we're going to talk about lesson 27, which is valence bond theory and hybridization. So valence bond theory really comes from the fact that if we think about drawing methane, CH4, we might anticipate that the 90-degree angle between the carbons and the hydrogens might be what we would expect to see, but we know from previous lessons and with above molecular geometry that that's not what we see. Okay, right, this is our known tetrahedral structure for carbon and 4 hydrogens. And we know that the bond angle is at 109.5 and not at 90 degrees. So, theory, actual. Okay, and so the reason why this came about was because we needed to understand why we saw this and not in theory. Okay, and so from this we're going to see that valence bond theory is going to lead us to sigma pi bonds, hybridization, hybrid orbitals, and then comparing that back to electron pair geometry. So this is really just adding an extra layer. Now the rest of this chapter, chapter 8, 8.3, and 8.4, focuses on molecular orbital theory, which we're not going to cover. So we're only going to focus on the first 2 sections of this chapter. But the stuff that we're covering really just continues to build on the stuff from chapter 7. So take about 2 minutes and discuss with your neighbor these questions, and then we'll go over a few of them before we start lecturing today. So take about 2 minutes. Okay, ready? Give y'all a few seconds to get ready. All right. So, in order to talk about these questions, we have to remind ourselves about something we learned a few lessons back, probably actually better to say the very beginning of the semester, when we talked about the S, the P, the D, and the F block. Okay. Now back then we just really used it, we've used it for a lot of things, to describe where the location is, to use them for electron configurations, and now we're going to use them to describe bonding. Okay, so S orbitals are spherical in shape. P orbitals, they get referred to in different ways. You have the dumbbell, the bow tie, the barbell, and there are 3 of them. There's one that'll point along the x-axis, one that points along the y-axis, and then the z-axis, it's going to point out. So it's kind of pointing towards you, out and towards the screen. Okay. Now the d orbitals, remember we talked about there being 5. Okay, so most of them, 4 of the 5 are clover shaped, and and then there's one oddball out, which is shaped kind of like a p orbital, but with a little ring around the center. Okay. Now we don't really focus on the f orbitals. We're only barely going to get into the d orbitals as it is. So now that I've reminded you about the shapes, we need to think about what types of overlap of those sp orbitals can form a sigma bond, which also we think of as a single bond sometimes. And there are three types. The first is that two s orbitals will overlap. The second is that an s orbital and a p orbital that's on its side will overlap. And then the third is that a p orbital that's on its side by another p orbital will overlap. And you can see where the orbitals overlap. That's what we're talking about, the formation. Okay. Now d orbitals have the potential to do similar type bonding, but we're not going to get into that specifically. We're going to kind of leave that for future discussion maybe in another class. So these are our three options for forming a sigma bond. Okay, a little sigma. Now the pi bond, the only one we're going to worry about is the overlap that occurs between two p orbitals that are side by side. So instead of being end on end, they are side by side. And you can see that there's potential to overlap in both lobes of the p orbital. Okay, so that's going to be our only pi bond that we're going to focus on. So we have a rule about how this relates to single, double, and triple bonds. Okay, single, double, and triple. All single bonds are made up of a sigma bond. All double bonds are made up of one sigma and one pi. And then every triple bond is made up of one sigma and two pi bonds. So you can see that a single bond is 1, double bond is 2, triple bond is 3. Okay, so let's practice applying that to this molecule. So you have to be able to draw the Lewis structure. And then it says, look at the image on this page right here. This will be helpful if you are still unsure. I would recommend looking into your book for further help. So now that I've drawn the correct structure, I'm going to count how many sigma and pi bonds I have according to this little rule that I just gave y'all on the left. So the hydrogen-carbon bond is a single bond, therefore it's 1 sigma. The triple bond between carbon and nitrogen is made up of a sigma and 2 pi's. So therefore my total count is 2 sigmas and 2 pi's. And in this case, non-bonding electrons do not count towards this. Okay, so we can ignore them when we're looking at sigma and pi bonds. All right. So let's think about our carbon example up here before we fill in this table. So if we think about the electron configuration of carbon as it is on the periodic table, we know that it's 1s2, 2s2, 2p2, right? So we've drawn this before. This is not new to us. And this is how we would fill it in correctly. Now, when we look at bonding, we can ignore 1s because this is the core. So really, we're only paying attention to the valence shell, which is the 2s and the 2p orbitals. So when carbon goes from carbon by itself to carbon plus something else, we'll just put Y, it undergoes what's called hybridization. I'm going to need more space. Okay. And what happens to these outer shells is that instead of being of different energy levels, right, we talked about this being with respect to energy, lowest, ground state, highest. These 4 outer subshells no longer are unequal in energy, but then they become equal in energy, and we call that degenerate. Okay, under the conditions of carbon forming a molecule, creating a bond with another atom. So what that means about our 4 valence electrons is they're no longer filled the same way they were, where 2 are in the 2s and 2 are in the 2p. Instead, 1 is distributed to all 4 of the sp3 hybridized orbitals, s, p1, p2, p3. And now this is where the actual structure is predicted from. It's why they are equally distributed at 109.5 degrees and why it does not adopt this 90-degree geometry that we might expect if we looked at it when carbon was not in a bond, when it was by itself, when it was not in a molecule. Okay? So this happens when any atom forms a bond with something else, a covalent bond. Okay? So it doesn't just apply to carbon. But what that means is we have a set of rules, a pattern that arises from this. Okay, so it's not like each element is going to have its own set of hybridization rules. And so we're going to fill this table out, which will help us predict all atoms' hybridization. So in this case, we can go ahead and fill out the sp3. We know that carbon is tetrahedral. It forms 4 bonds. That comes from 4 hybrid orbitals. Okay, we see those right there. And we know that it comes from 1s and 3p because we've already written that out. We got that from the electron configuration. So let's fill in the rest of the table because there's a pattern that will arise. sp2, 3 hybrid orbitals that form. 3 bonds can form. We know this as trigonal planar. Right? It's our electron pair geometry name, that first column in our table from a few lessons back. This is going to come from 1s and 2p orbitals. If we look at linear, it's 1s and 1p. This is 2 orbitals that will form, 2 bonds that can form, and that's what we know as linear. And this is sp hybridized. If I work back the other way, once I leave the P block and I've used my PX, my PY, my PZ, then we know that the next step is to move down to the D block. So now I'm going to start having access to D orbitals. So now I have 1D, 1S, and 3P. This is something that has 5 hybrid orbitals that form, meaning 5 bonds are possible. And this is our trigonal bipyramid, our trigonal BIPY. Okay, and we call this DSP3 hybridized. Now the last one, this is typo. This should be 6 hybrid orbitals that form, 6 bonds that can form. We know this is octahedral as the electron pair. It's D2 sp3 hybridized, and that is formed from 2 D orbitals, 1s, and 3p. So we're just adding on, just going across the periodic table like we did with electron configurations. Okay, this table you need to know. It's important. Though the patterns should match up really well. You can actually go back to your lesson 26 table right here and add the hybridization to your table because it's not really adding a whole new concept. All it's doing is continuing to build on something we've talked about. All right, so let's move on to the lecture notes today. We're going to practice pretty much everything we learned up above. So a friend tells you that nitrogen has 3 pi bonds due to the overlap of 3 p orbitals on each nitrogen atom, and do you agree? So the first thing we need to do is draw the nitrogen structure, which is 2 nitrogens with a triple bond between the both, and 2 non-bonding, one pair on each nitrogen. So according to our rule up here, we said that triple bonds are made up of 1 sigma and 2 pi's, meaning that my total count of pi bonds is not 3, but it's 2. So I would not agree that it's made up of 3 pi bonds, but I would agree that it's made up of 2 pi bonds, 1 sigma bond, giving me a triple bond. The next one, it says to draw 2 Lewis structures and predict the number of sigma and pi bonds. So if I draw my structures out, I'm really only focused on the central atom. So in this case, I have S and P. So we would say this is sp hybridized, but my double bonds are made up of sigma and pi. Sigma and pi. That's my double bond rule we'd set up above, meaning the carbon dioxide is 2 sigma and 2 pi. And then my carbon monoxide only has the 1 double bond, therefore it's 1 sigma and 1 pi. We're going to have very similar questions on the test, except for I'll show you what the format of the test will look like, what it will look kind of like when we get to the bottom. So explain why a carbon atom cannot form 5 bonds using sp3d hybridized. So in order to answer this, we have to look up here and ask ourselves, well, where are the d orbitals? Okay, so if we think about that, carbon does not have access to d orbitals. Therefore, it cannot form 5 bonds using, let's make that look right, using dsp3 hybridized orbitals. So before we go on, I want to point out that writing it sp3d and dsp3, there's no difference in that. It's just the arrangement, but it's telling us the same thing about hybridization. Okay, so we know that once we get to period 3 elements, these are the ones that can have expanded octets, and that was because they have access to d orbitals. Carbon's in period 2, therefore it's not able to form 5 bonds and have an expanded octet. All right, so hybridization. We're going to determine the hybridization of each central atom in the following. In order to do this, you usually need to start off drawing the Lewis structure, and then we'll look for a pattern after we draw our Lewis structure. So in this case, beryllium with 2 hydrogens. Beryllium has 2 electrons. It's going to give 1 to each hydrogen and form 2 covalent bonds. So the way I usually do a hybridization is I just go in order around the bonds. I have 1 S, 1 P. This is sp hybridized. It's linear, so I could also predict based on the linearity of the structure that it is sp hybridized. If I do sulfur hexafluoride, because I'm not worried about the correctness of the Lewis structure, I'm not going to add the lone pairs around the fluorine because I'm only focused on the sulfur. And if I do this, I have sp1, p2, p3, d1, d2. So this is d2 sp3 hybridized. I'm going to highlight that. There we go. Okay. It's octahedral, so I might have predicted based on that this would be the correct structure. Phosphate, it's one of our polyatomic groups. If you think back to when we did Lewis structures, we said that anytime we have like this negative charge up here and we have oxygens present, that's usually because we have a single bonded oxygen. If we have 3 negative charges, means normally 3 of our oxygens are going to be a single bond with that 3 non-bonding electron pairs and the bond. So in this case, I'm going to have sp1, p2, p3. So S, then a p1, p2, p3. Tells me this is sp3 hybridized. So the important thing about this one is to remember that this double bonded oxygen occupies a single site. Therefore, it's not going to be counted as separate bonds. We're not counting it as S1 or S and then P, P1, P2. It's going to be as a single site. So it gets one hybrid orbital in that area. Okay. Last one, PCl5. So at this point, you might start to see patterns and you might predict the hybridization. And then if you haven't yet, I will tell you one way you can do that. It's got 5 bonds. Each chlorine is evenly distributed around the phosphorus. So it's sp1, p2, p3, and then a d orbital. All right, so a quick check is that sometimes the subscript behind the second atom will relate really well to the hybridization because of the number of bonds. Okay, it's not always true because we're going to see how lone pairs on the central atom can affect this. But if your structure doesn't have any lone pairs, the subscript behind the second element will describe the hybridization. Okay, so it's kind of a quick cheat if you're running out of time on a test and you just want to guess. You could try to use that and it might be right. But if you have lone pairs on the atom, it's going to change the hybridization. Okay, but if there's no lone pairs, the subscript behind the second element will describe the hybridization. All right, so now let's do the next question where the lone pairs will have an effect. So the question reads that a molecule with the formula of AB3 can have one of 4 different shapes. It says give the shape and the hybridization of the central atom for each. So the way that this becomes possible is because of the lone pairs on A. Okay, so in this case, we have an A atom with 3 B atoms evenly distributed around in our trigonal planar. We know that this is sp1, p2, so this is sp2 hybridized trigonal planar. Okay. The next one is when we have our tetrahedral structure that then loses one atom and is replaced by a lone pair. So this is very similar to ammonia. We know that this is tetrahedral as the electron pair, but trigonal pyramid is the molecular name. And this is sp1, p2, p3 hybridized. Okay, so the lone pairs affect hybridization. The next one is where we have our electron pair of trigonal BP, where it's lost 2 atoms and 2 lone pairs have been replaced on the central atom. So it kind of looks like a fan. And then we have our lone pair here, right? The axial. The equatorial atoms are lost and replaced by lone pairs. So this is still trigonal planar. And it is sp1, p2, p3, and d hybridized. Now the last one is derived from the octahedral structure. And this is probably the hardest to draw. Excuse me. Let me do this a different way. you go. Perspectives are hard to make sure it looks like what y'all would expect. So if we think about octahedral. Okay, so I put electron pairs here and here and here, and the B's are here. Okay, so this is called T-shaped, but it is SP1, P2, P3, D1, D2 hybridized, which is D2, SP3 hybridized. Okay, so lone pairs did not have an impact on sigma and pi bond counting, but lone pairs on the central atom affect the hybridization, just like they did the molecular geometry. All right. Write Lewis structures for NF3, PF5, and on the basis of hybrid orbitals, explain the fact that NF3, PF3, and PF5 are stable, but NF5 does not exist. So NF3 is going to look very similar to ammonia. It's a very common structure for nitrogen to adopt, where it has 3 bonds in a lone pair. And phosphorus is capable of being hypervalent, meaning it can disregard the octet rule and have more than 8. And we can go ahead and even draw PF3. I don't think that will hurt us. It's going to be very similar to the NF3 structure we have on the left, except for phosphorus is now the central atom. So the problem with this is that if we think back to our discussion about carbon, it's very similar. The reason why phosphorus can adopt either a 3 bond plus 1 lone pair or a 5 bond structure is because it has access to d orbitals. Nitrogen, on the other hand, only has access to s and p orbitals, which, very similar to our discussion about carbon, means it cannot form 5 bonds and be stable because it cannot form this. Okay, it's not possible for nitrogen, but it is possible for our period 3 elements, which we've already just set up here. Okay. So period 1 and 2 are limited to structures that can only be sp3 hybridized or lower. And then once we get to period 3 elements, for our covalent compounds, they can form sp all the way up to d sp3 and d2 sp3. Okay. All right. So this next thing is an extra worksheet practice. So my goal is to work through one example, and then leave you with these to practice because this is what you're likely to see on a test, on short answer stuff, okay? So I want to give you a chance to practice, and then I'll post the answers to this at the end of the... Well, they're probably already up on Canvas, to be honest, but they will be up and available to you. And then I'll leave you with some time to ask questions. All right, so first we need to complete the structure. We know that carbon and oxygen are not likely to form just a single bond, so we know that's a double bond. And we need to go ahead and put in our electron pairs. Okay, so my structure is complete. This is acetic acid. And now I'm going to count the number of sigma and pi bonds. So I have sigma, 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 sigma. It's 1, 2, 3, 4, 5, 6, 7 sigma bonds. Now because I only have one double bond, it means I only have one pi bond. Okay? So that's one of the first things you need to be able to do. The second thing is looking at the atoms that are marked here, predicting the bond angle, which we got back from our previous lesson, and then hybridization today. So or atom number 1 is the oxygen. It has sp2 hybridized because it has a single bond, a double bond, but it's a single site occupied by a bond, and then 2 lone pairs, so it's sp2 hybridized, meaning the bond angle we would predict is 120. So that's our trigonal planar geometry. Number 2, let's see if I can zoom in this a little bit more, has sp1, p2, p3 hybridized. It has 2 bonds around that oxygen and 2 lone pairs. So this is sp3 hybridized, and we would predict 109.5. Number 3 is this carbon. It has sp2 hybridized because the carbon only has really 3 bonding sites occupied. One is a double bond, and then we have 2 single bonds. So when we have sp2 hybridized, we predict 120 degrees. Okay. So I'm going to draw those out. So we have sp2, sp3, sp2. Okay, so just layering what we've kind of talked about in the last couple of lessons. All right. So this is something you'll expect on the test with the exception of the last question. Okay, so we've not talked about what it means to be planar, but I will give you a structure very similar. It's going to be a complex structure. You'll have to, I didn't do a very good job of erasing. You'll have to go in and fix anything like the lone pairs are missing. So it's good practice for Lewis structures. Nitrogens, 3 bonds and a lone pair. And then all the double bonds are drawn in. So let's practice the carbon. So this says how many carbons are sp3 hybridized. These are going to be carbons that have 4 bonds. So I see 1 carbon here, 2, 3, 4, 5, 6, 7, 8, and that's it. So I have 8 that have 4 bonds. Now sp2 hybridized means carbon's only going to have 3 bonding sites. So in this case, I see this carbon, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm looking for carbons that are, this is tetrahedral, this is trigonal planar. Now when I'm looking for sp hybridized, I'm looking for carbons that are linear. And if I look through my structure, I realize all of my carbons have been accounted for. So there are 0 carbons that are linear, that only have something like this. Okay. There aren't any. How many nitrogens are sp3 hybridized? So this would be nitrogens that have something like this going on. So if I look for that, I see the nitrogen here, 1 and 2. Both of those nitrogens have 3 bonds and a lone pair. If I look for sp2 hybridized, I'm looking for nitrogen that has 2 bonds, like this, and 2 bonding sites and a lone pair. So 1 and 2. And then if I look at sp3 hybridized, I'd be looking for nitrogens that are like that, and I don't have any that are terminal that's 0. I've already accounted for all of my nitrogens. Okay, so now we're going to focus on oxygens. So sp3 hybridized oxygens would be ones that are like this. 2 bonds and 2 single bonds and 2 lone pairs. So in this case I have 1, 2, 3, 4. I don't see any others. And I realized my electrons are not on these carbonyl groups. Now I need to look for sp2 hybridized. These are going to be the ones that are like this with a double bond and 2 lone pairs. So 1 double bond and a lone pair. In this case I have 2. And then sp hybridized oxygens, I have none. Then it says how many sigma bonds are there in total, how many pi bonds are in total. The hardest part about this is missing one. So I usually go through and I'll say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So then I know in this section I have 20. That way if I make a mistake I can come back. So then I'm going to start with the ring. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. And then I go back through and I make sure that I've crossed through all of my bonds. Because if I've crossed through all of my bonds, I have counted for it. So 52. Okay. Now the nice thing about your pi bonds is we're only looking for double bonds and triple bonds, which can get kind of confusing once you've drawn all these lines through it, but hopefully it'll be easy enough to see that this is 1, 2, 3, 4, 5, 6, 7. Okay. So this is your paper on your test. You can mark all over it if you want to. The nice thing is you are going to practice using the acetate ion. Some of the stuff we've talked about, the Lewis structure and resonance, hybridization around each carbon, pick the resonance and identify oxygen, counting sigma and pi, and then which atom carries the formal negative charge. These are all things we've talked about. It's a great cumulative question. Okay. But for sure, you're going to see something like this on the test. Different structure, but very similar. And then this is great practice for those questions. Okay. So you should have about 10 minutes left to ask Dr. Spencer questions or Dr. Morris, so don't pack up and leave. Make sure you ask questions about this material. The YouTube video will be available to you guys already, but just make sure that you take this opportunity to ask with somebody there in the room. Okay? All right, I hope all is going well.